Alrighty. Share screen. Oh, I need a video again. Alright, could everyone see the screen?
Yep.
Nice.
Yeah.
So here's our GAN mini lecture. So GANs, we talked about them a little bit in the past, I think, just touched on them. But these are generative adversarial networks in which we have a generator network that is producing fake images from noise, and a discriminator network that is deciding whether an image input is a real image or a fake image. So these are two networks kind of fighting with each other, and by doing so, they're both getting better. As you can see, we do need to make this work a number of real images. These are going to be whichever images, whatever type of image that we're trying to create. So if we're trying to generate images of an airplane, we're going to have a lot of airplane images, and the generator is going to be trying to copy those without seeing them. The generator never gets to see these real images, in fact. The generator is going to get, because neural networks tend to be deterministic, it is going to get a d-dimensional noise vector. There's a lot of selection that goes into how big the noise vector is going to be, but frankly, from what I've seen, it doesn't matter all that much. You don't want to have just like one variable or one value or something random, but you don't have to have it be huge either. It's just going to be a vector of random noise, and it's going to help us have some randomness in what our image looks like. So again, the generator, this is going to be mimicking a function that maps random noise into some image or some other data record that belongs to the class it was trained on. And it's going to actually use the discriminator as part of the loss function. Basically, if the discriminator can tell it apart from a real image, then it's going to be punished. It didn't do as well. And if the discriminator can't tell them apart, then it's rewarded. It did well. It's going to have a smaller loss. And the discriminator is just basically just a kind of weird niche classifier, binary classifier deciding either is this the real image, that's going to be a 1, or is this a fake image, 0. So we're going to run through this one mostly just by looking at the code, because the model itself, the nice thing of this model kind of just makes sense intuitively. We have a generator and a discriminator, and the discriminator is acting as a critic to our generator, basically. Technically, there's something called a critic that's even better and more powerful than a discriminator, but it's a simplified version. By the way, this is all in TensorFlow 1, or not TensorFlow 2, it's TensorFlow 1 point something. And I think the GAN lab ended up being made in TensorFlow 1 as well. So when we get to the actual lab for that, you're going to have to either convert it to TensorFlow 2 or go back to TensorFlow 1 point something. Apologies for that. We'll try to fix that in coming semesters, but for now, that's it shouldn't be too bad, especially because you can use virtual environments, so it should be pretty easy to just grab a version of TensorFlow 1 point something.
At least for the moment, TensorFlow 2 has a compatibility bit so that you can use things from TensorFlow 1 in it.
Oh, nice. Okay, you can do that too then.
It just requires some conversion of code to make it work properly.
Yeah, I'm remembering because this. What made me remember is that this has the imsave thing from SciPy, which is not TensorFlow, but apparently that's been deprecated. But there's a post on that on Piazza, so if you want to change that over, you can do it that way, or use an older SciPy, however you want. But anyways, first thing we're setting up our imports and everything. We're using a lot of the same things that we've used before. Dense layers, reshape, flatten. We have batch normalization, which I think I might talk about in this lecture somewhere. I have to find it again. But leaky relu. Anyone remember what leaky relu is? Any guesses? All right. Well, that is an activation function that is it's relu, but it has a little bit of a tail on the end that goes into the negative, and that tail is very, very small, so that it still negative losses still don't mean much, but you can still gradient descent along that instead of it just being 0.
How does that compare to ELU?
If I remember correctly, ELU is doing. It's got kind of a curvy tail. It's doing something. I think logarithmic. No, could be. Is it a square root? Something like that. It's got a curvy tail versus leaky relu, which has just a flat linear tail. I'd have to check back again, but
okay.
Yeah, we'll do that at the end. But yeah, in this case, we're also using MNIST, which I think it's somewhere here. Regardless, you can see it from that pretty easily. We have 10 classes, 28 by 28 images, and in this case we're using a noise size of 100. So here's our main pipeline. We're getting data. We are going to build a GAN and train it from that data, and then we're going to run it 10 times to get some outputs. So this is more or less what you're going to see in the main function of your lab. When we get the data, we're going to do some very basic pre-processing. We're just doing our squishing it down to between -1 and 1. This lets us do our tan-H activation. And we're returning this nice image data set here. Then we build our generator. In this case, we are using this sequential. 3 layers of leaky relu with batch normalization, and then the final layer we're using our tan-H. And this is going to bring us to that between -1 and 1 range that we've compressed all of our images into already. And that's going to, once we're done with that, we reshape it back into the shape of our image. You'll also notice I didn't do any convolutional layers here. In the lab, you can choose to do it this way. You will get slightly fewer points if you do it this way, though. If you can do it with a convolutional neural network, then you get full points. But with dense layers, it should be still pretty doable. And that's it. Then we return this model, and we're good to go. Yep, those are our 3 layers. or leaky relu, leaky relu, leaky relu, and then tan H. Ah, good, I do talk about batch norm. Okay, so in batch normalization, what it does is it's subtracting the batch mean and dividing by the batch standard deviation for that whole batch. And that's going to normalize the outputs of that layer to make it so we don't worry about extremely large outputs. It kind of forces everything back into a certain range. And that can be very good for an issue called internal covariate shift. Not going to go super into that because that's just a whole nother subject. But here's an article on that if you want to look into exactly how that is helping internal covariate shift. For things like this, and for a lot of things really, batch normalization is a really good thing to have. In fact, I think most like industry models are using batch normalization somewhere. Now we have discriminator.
Quick, sorry.
Oh yeah, question?
Quick question about the previous one, the batch normalization. So would that just be recording the z values then for everything?
Oh yeah, that's going to be recording those z values. Okay. Actually, technically, I think it's So that's actually happening after activation. So that's the activated z values.
Okay. Interesting.
So it's still going to be within that range, but it's going to be within the activation range, but it's going to still do batch norm after that.
Mm-hmm.
So discriminator. What this thing's doing is we have our dense layers and our leaky relu layers again, but this time all we're doing is at the end we're having a sigmoid layer. Can anyone guess why we're using sigmoid for that?
Sigmoid would provide between 0 and 1, so it would be sort of able to guess a probability, I believe, or a confidence level.
Yeah, sorta. So it's the reason we have it be between 0 and 1 is just because we're treating it like a binary classifier. So yeah, 0 is going to be no, these images are one of these images is fake, or 1, this image is real, and anywhere in between we are going to be going to the closer one. So yeah, we're looking at like a confidence level. That's a good way of putting it. So we return that model. Oh, hey, there it is. Yeah, I was right. So there's our leaky relu. If we had an elu, instead of it being just this line here, we would have kind of a sloping sort of thing down, but it would still have very similar behaviors. The nice thing with elu versus leaky relu is you can see we have a gradient here, and we have a gradient here. We don't have a gradient here, and elu is going to have that because it actually slopes and continues down that way. But this one, we still, versus relu, would just have no gradient here either. So we've gone from half of all integers, basically, all the negative numbers not having a gradient, to only one specific point not having a gradient. Finally, we build our GAN. This is going to be, first of all, creating our discriminator and our generator. We've called both of those functions here. We've decided to use atom optimizer and binary cross entropy, specifically for the discriminator. And the discriminator, we can compile it pretty simply because it's just a classifier again. We're also going to set it to not trainable right now, so it won't actually update the weights for the moment. We create our noise tensor here. We create a model for our GAN, and we are combining, for the actual GAN itself, what we're doing is we are saying that it is the discriminator that is taking in the generator that is taking in noise. So when this computational graph runs, it's going to put the noise into the generator. Generator runs, outputs an image. Image goes into the discriminator, and that is our model. And of course, our input to the model as a whole is going to be noise. And remember, we're working with computational graphs here in Keras. So when I set this up, this isn't actually running the model. This is just describing how our model is going to end up working. It's building the graph. We compile that with loss and with our loss function again and our optimizer, and we can get to training. So for this training, first of all, we're going to have a truth column. These are going to be just ones. They mean that this is actually for real our image, and it's from a data set, it's not generated, and a false column, and that's going to be this is not from our data set. This is something that the GAN generated. Next, we run through our epochs. Let's see, actually, no, I don't go over those. We run through our epochs. We get a batch size or a batch. We make some noise with our np.random, and we can use our generator.predict to create these predictions, put them into our discriminator, and see how we do. We use this train on batch function, by the way, to just do one batch at a time, which is helpful for this sort of thing. And as you can see, that is going to train the discriminator one time, but on two different images, one on a true image, a real picture of a plane or whatever, and one on a false image. That is going to be some, at this point, at the start, for the discriminator, probably, or the generator, probably just looking like white noise. It's not going to look like anything. We are going to adjust our loss with that, so we can do our back propagation. Well, it's already done it, but we're going to generate the loss there. And then we get to training the generator. Oh, wait, do I only have? Yeah, it's only that. The generator, all we're doing is we are going to take in our random noise, and we're going to train it on that noise batch and see if we can get it to match what the discriminator is doing. Next, we run our GAN. What that's going to do is just run the generator. You can see we're doing a generator.predict, and we have to scale that image back up because we before did our whole bringing it between 1 and -1 thing. And then we can save it. And we get these results, which are pretty good, right? I mean, they're not perfect MNIST ones, but you can see the kind of numbers that it's printing out here. And it's nice because this one is actually trying to print out different numbers. One problem you might run into is if you want to train the whole MNIST, it might end up just going, oh, well, 3s are easy. I'm going to always print 3s. This one doesn't do that, which is nice. But yeah, though sometimes you want that. In fact, in our lab, we're not having you do any sort of making GANs where it's You're not going to have to make any GANs that are doing a lot of different classes. It's usually just one class at a time. A lot of variants out there. We're not going to talk too much about any of them, but there's something called the Wasserstein GAN, which can improve stability. This is what I was talking about with the critic. So instead of having a discriminator that's just saying 1 or 0, basically, or we're eventually bring it down to 1 or 0. This one is going to leverage something called Wasserstein distance to implement this dynamic critic, which can give us values between negative C and C, where that C is just a number we're putting in. There's something called a WGAN with gradient penalty. This replaces the weight clipping that we had for the Wasserstein GAN with gradient penalty. Basically penalizing the model if the gradient norm moves too far from the target that we're looking for. And then the really interesting ones down here. CycleGAN, usually used for image transition. Case talked about it just a little bit. It was made by some guy at Adobe. And it's good stuff. It uses 4 networks instead of 2, though. And it can do things like if you have a video of a horse running around, you can make it look like a zebra. You could take an image of a mountain in summer and make it a mountain in winter, and that's pretty cool. It works supremely well. Very good, interesting. Oh no, is that StyleGAN that does that? Case, are you still here?
CycleGAN.
That was CycleGAN. Cool.
Yeah, the cool thing about CycleGAN is when you train it, you don't need like exact paired images for like summer and winter. You can just feed it in pictures of summer and pictures of winter, and it'll learn what that means.
Yeah, it's really cool stuff. BigGAN, honestly, one of the biggest reasons that I left this in here is I love the name. It's perfect. It's what it is. It's a really big GAN, and they called it BigGAN. It's awesome. But yeah, it was for a while considered state of the art for image generation. It's very good. And then StyleGAN, which actually uses style transfer concepts like the ones that you've been working with to generate images. So good stuff there. And here's some of CycleGAN. So we have our horse turned into a zebra. Like that's pretty effective, right? Yeah, it's able to do that pretty well. Or zebra to horse. There's zebra to horse, zebra to horse. I think horse to zebra looks a little better than zebra to horse personally, but still pretty good. Here's BigGAN's image generation. These all look completely realistic to me, but
I think the dog's eyes look a little weird.
Yeah, but I think they have reflection in them. The dog one is definitely the most like I'd take a second to be like, huh, what's up with that? But then like the sandwich one, like this one here, like I can't see. Like if I saw that, if someone sent me a picture of this, I'd be like, oh, what are you having? You know?
Definitely. Looks very realistic.
Yeah. StyleGAN, we saw this one before. This was our one that uses our style transfer concepts to generate faces, or one of the things it can do is generate faces. And it has some really good ones in there. This one particularly is quite good. And that's it for GANs. So more links.
Keep in mind that with StyleGAN too, if you wanted to train it on one graphics card, it would take 70 days. And that's one like Tesla V100. That's like a $10,000 graphics card.
Holy cow.
Some questions here I didn't see yet. What is the reason we are using range of -1 to 1 instead of 0 to 1. Um, well, the reason in this case was because the implementation I found before was doing that, so I was like, yeah, why not? But I don't know exactly. I think I don't think they all do that. Um, my guess would be is it gives it a little bit of a better range of generation, so it can kind of make more mistakes almost, or make it a little more resistant to mistakes. That's my guess. I don't know though. I'd have to. I'll check that out though, and hopefully get
There's an
an
actual
answer.
reason. I forgot why, but they found out that flipping it to -1 and 1 opposed to 0 and 1 had a big improvement.
Oh, is there article for that or something you can?
I can find it. It was in the GAN book I had.
Oh, nice. Yeah, see if you can dig that up. And that's pretty much it for today.